I've never done this before, but I'd like today to begin today's lesson with this thought experiment. If it goes wrong, know that I won't do it next year. You know, I don't know. Next year's kid won't be. But let's see how this goes. I'm just trying this, okay? Just for fun. All right. So, say you have a factory that has W of D workers on a given day D. That number changes because of their schedules and because you like to fire them and stuff like that. Is that okay?
Yes.
So far, so good. Also, every worker has efficiency E of D. That is, they produce E toys in a given on a day D. We can reasonably expect that to fluctuate too, because of various outside sources. I don't know. Whatever else. Maybe they're just tired. All right, so now I want you to think hard about what this function means. WE, that is the product WE. What does that do? On a given day, D, what happens when you multiply the number of workers by the number of toys each one of them produces? Yeah.
The number of toys produced total.
Yeah, so WE is a meaningful function in our lives. It's the product of these two functions that represents at any given day, on any given day D, the total toy output of the factory. I haven't lost anyone yet. Now these three functions are a little harder to describe, but I want you to try. W prime of D is, anyone want to try to articulate it? Go ahead, Cameron.
The change in workers in daily day.
Okay, so yeah, if W prime of D is positive, yeah, the number of workers is rising. It's on the rise. If W prime of D is negative, then it's falling, right? The number of workers is falling, etc. What about E prime of D? Explain that one, Piper.
It's the efficiency is increasing or decreasing day by day. So like
Yeah.
Yeah, if it's positive, then the efficiency is increasing.
Yeah. And then you want to take the last one, Siobhan?
Just the total number, like whether the total number is increasing.
So I hope you understand that the 6 functions we just talked about all have very meaningful uses in our lives. Right, Franklin? Yeah. So now I'd like you to think about how they relate, if they relate at all. What should this total, because we're very interested as the manager of this factory or whatever, the owner of this plant. We're very interested in this very last function we mentioned, WE prime, the total change in the output of the factory. Because, for example, if I could figure out a way to make it positive, I could be increasing my, right? If I can have some control over that, that would be really cool. So, better yet, maybe we can even come up with a formula for it. So, what should it depend on? I want you to think hard about this. How would you actually calculate that? I mean, if we change it, Siobhan, you have an idea?
Once we multiply like the rate of change of efficiency by the number of workers.
Why?
It sounds right.
Okay.
Like, yeah.
Well, she can't figure out how I tell us that is right, and then we can't do it.
Well, I want it to be intuitive. Otherwise, this fails. I won't do it next year if we can't land this. I mean, it's worth saying too. I think maybe it's still worth it. But yeah, what should that depend on? For example, say we increase by just a little bit the efficiency of each worker. How much of an increase in the total output of the factory?
A little.
No, be very precise mathematically. What is the change? It's not just E prime of D, right? It's times what? Times the number of workers, right? It's the number of workers times whatever the small change in their efficiency, all of them was. That's the increase. Okay, what if we also, though, change, we're tweaking both formulas here, right? What if you also increase the number of workers by a little bit or decrease it? How do we account for the change in the total output, the toy output? Say it again.
Multiplied by the efficiency.
Yeah, by the current efficiency of all the workers times the change in the number of workers. That gives you a sense of how many toys less or greater than they were doing before that you would get. So do you have a formula in mind, Johnny?
Okay, right now are we talking about W E of D or W E prime of D?
W E prime of D. Yeah,
Like,
we're wondering how it relates to the other things up there.
Because you said like you multiply like the two other functions, but like if you can multiply them to get W E prime of D, then that means that if you had a negative value for W E prime of D and E prime of D, then you still have a positive output of
Wait,
stuff.
no, we said, so what, yeah, how are we gonna get this? Let's say it again. Does someone have the completed thing we said?
Does he have it?
Do you?
It's like, it's not really, it's hard to, like, include both variables at the same time.
Go ahead, Jack.
Does W of D times D prime of D like or W of D or E of D times W prime of D like we use?
Yeah, no, if both are changing, then we can do what with them? Yeah, we can add them up. So I'm going to give you this formula now finally. Again, those who had took AB last year, how did I do with introducing this rule? You didn't like that? Okay, I'll never do it again. Good. All right, thank you for the feedback. All right, I just want to, my attempt there would be, though, to provide some intuition for why this is true. And then I'll have a formal proof on the next slide for you to look at, too. But it's not very illuminating, okay? Well, you come up with a better one, and I'll put it on my slide next year, Haley, okay? Yeah.
I think it might be better to do that
After you do this.
Was my point that I said
Yeah.
that
Explain why this makes sense in that situation or something. All right, all right. Thank you for helping my teaching. Okay, so the product rule says what we've just said, and that's that the overall change in a product of two functions uv is equal to u times the derivative with respect to of v with respect to x plus v times the derivative of u with respect to x. If you drop all the independent variables, you can just write it more simply this way, if that's understood in the situation that we're talking about. But please notice, at the very least, that it's not true that it's just the product of the two derivatives. So try it. Try it with this set of functions, and I'd like you to try it both ways, because this is a function that even last night you could have taken the derivative of without this rule by doing what first? Yeah, you could just multiply it out. So try it both ways and just see if this product rule seems to be working at the very least, okay? Do that, and we'll come back together in a minute. Yeah, Piper. Pass is over there right now. But I want elimination.
Like give it, so like, so you have nothing to compare.
Well, everything should make sense, though. Don't you think it might?
Well, should does not mean does. Yeah.
That's how I used to think, but then I just decided it's better to just follow the rule and not question it for math class.
Which is like this is the first time I've heard it actually.
Where did my where did my pen go? How's it working for you out there? Does it? Who is done with one of the two tasks?
Move, please.
Actually, which one do you have? Would you like to put up? On the left. Leave room on the right for someone. She's multiplying it out and doing it the old school way without the product rule. Has someone got the product rule there? Thanks.
Wait, I don't know if we did it right.
Well, we'll see.
Wait, guys.
Maybe, do you want to just skip the work?
Sure. So just write the.
Yeah. Just write your final answer. Derek, you coming up? So, I want to make sure everyone's using the product rule correctly, right? You understand you're going to take this function and multiply by the derivative of this function plus this function times the derivative of this function, right? Said out loud, yeah, hit the pen. Then hit eraser. And then go back down there for the pen. Said out loud, it's like the function times the derivative, f times the derivative of g plus g times the derivative of f, right? I think it's easy to remember. This is the final answer you get if you multiply it out, she says, and then take the derivative. And Derek has the final answer if you do the product rule. They did these beforehand without consulting with one another. We're going to see now, studio audience, whether they came out to be the same. It's so exciting. No, you don't know. We didn't have them show the work. So, did you get the same thing?
Did I simplify that right?
I don't know. Just keep writing.
14 plus 23. Wait. 23.
What's your answer?
I got 37x squared.
You get 33.
Can someone confirm the first result?
10x to the 4th plus 33x squared.
Which one's wrong?
I multiplied 5.
On the left, it should be 33.
I said 5 times 3.
Okay.
Twice.
Can you fix this to be a 33 too? All right, so they do come out the same. Is that a 15 at the end?
Yeah. Yeah, sorry.
The picture of clarity. Okay.
Can I rewrite it?
No, it's all right. Everyone understands. Okay. And in fact, you know, the point is, the derivative is this, right? First times the derivative of the second plus the second thing plus the derivative times the derivative of the first, okay? And hopefully when you multiply this out all out, you get this, right? At this point in your life, I will say, it doesn't seem like you need the product rule, maybe, right? But you maybe just do that. But do know that there will come a time when the product rule will not be optional, and you'll see why soon. Okay, Haley. Okay. All right, go ahead.
It was instead of back to work for students, instead of making quiz, they were all like trying to talk about as many essays as they possibly can.
Okay, but won't we still have the same conceptual barriers?
Yeah,
though?
but you
It's more relatable.
You explain this first, and then use that.
Okay, all right.
And it's more
Okay.
relatable.
So I'm still new at teaching, you know? So, year 12, still learning. Okay, all right. I do not need you to write this down. I think it's in the book too, or whatever. But here you go. Here goes the formal proof of the product rule. Guess what? Guess what, guys? That's the definition of the derivative. Did you know that? Yeah. All right. Now here's the part that's a little crazy. Do you agree? You might not be able to see this from the back row. I apologize. Okay. But do you agree that we still have not changed anything? In red, we have what? 0. Yes. In red, we have 0. So it's a little strange, but do you agree that we can do that?
Yes.
I told you that this is a proof, but is not super illuminating, even though it is a proof in the end. All right. Next. Ooh, it is hard to track these parentheses. Okay. So what I've done over here is I've factored out a g of x plus h out of these two terms. Do you agree that if you multiply the g of x plus h back in, you get what we have up here? Likewise over here, I factored out an f of x out of both of those. If you multiply it back out, you can see that this is still the same as what we have above. All right, now,
What happened to the first f of x plus h?
f of x plus h here?
Yeah.
Yeah, it's still here. So when you multiply g of x plus h times this, you get this. And when you multiply g of x plus h times this, you get this. And this part over here is this part. Think about it. All right, I'm separating. I've decided to separate this now. This is the limit as h goes to 0. I'm splitting this right here at this plus sign here. So over here we have this, f of x plus h minus f of x over h times, oh wait, we still have a g of x plus h. Is it okay if I just have the limit on both of those? Limit of the product is the product of the two limits, isn't it? So we can do that. And then do the same kind of work over here. We've got the limit as h goes to 0 of this whole thing over h. And we can separate those things. Now, do you see why we're motivated to do all this now? What's this?
The derivative.
That is the derivative of what? F. What is this? As h goes to 0, what is this simply? G of x. And the same kind of reasoning over here. As h goes to 0, who cares? This is still f of x. And this is the derivative of g, the result we seek, right? Like I said, that's the proof, but it's not super illuminating. I don't know. So, all right, let's also derive the quotient rule. This one I am going to make you prove on your own. Okay? Where is it? Where did it go? Maybe I have it on the next slide. Okay. I think I have it. Maybe I have it on the next slide. Yeah, we'll prove it on the next slide. All right, let's try it down here. And I have where's my? Oh, this got stolen from me and didn't give it back. I gotta go find her. You do that. All right. So the derivative of a quotient, which we'll prove in a minute here, is this. It's easier to read over here, maybe. G times f prime minus f times g prime over g squared. A little harder to remember. You agree? A little harder to remember. Try it on the bottom.
Teacher's Teacher's gone. Let's
G prime. We already did that.
I didn't understand
Alright, there are not enough of these. I'll give these to you on Monday, okay?
Wait, are you got your own name wrong.
This is my thing. I made this document. We will, but I don't have enough copies yet. We'll do it on Monday. Yeah, is there an emergency?
Usually you just cancel things out.
I know, I'm a little sad that we don't have it. We'll do it on Monday. You want Want me to write on the board? All right. So what's the derivative here? It's bottom times the derivative of the top.
Where's Miss Getz, Mr. Chase?
6x squared plus 5 minus top f, that's an x, times the derivative of the bottom, all over the bottom squared. Okay? Now there might be some simplification work to do in this numerator, so we should maybe do that. The denominator we could multiply out, but I'm not sure that would be simpler, so we can leave that maybe. So we'll do it. Here we go. We got 6x to the 4th plus 18 and 5 is 23. What is that? 4x to the 4th. That's an x. Minus 10x squared. All right, this is a lot of symbol pushing, but here's a fine result. What do we get? Looks like 2x to the 4th. Help me out here. Plus 13x squared. Plus 15. Can someone confirm, please? Over x squared plus 3 quantity squared. Okay. All right, you did it. It is hard to remember, and I apologize that I don't have more of these. So maybe we'll do this on. I'll show you this on Monday. But I'll give you all a copy because Miss Getz, I promise, I had Mike stacked, and then Miss Getz was like, "Oh, I don't know where mine are. Can I steal them? I promise I'll make you more copies." And then she threw me under the bus like that. Okay. So the question is, what is the derivative of this? Is our easy, nice and easy way to remember this. Okay. The derivative. The question is, what is the derivative of pi over ho? And it's easy to remember that this is the thing that we would desire to take the derivative of, because pi is of course on top. Couldn't be any other way, right? All right. The derivative of pi over ho is ho, and by d high, I of course mean the derivative of high, don't I? Ho, bottom, times the derivative of the top. Ho d high minus pi d ho. That's the derivative of the top function times the derivative of the top function times the derivative of the bottom function, all over ho squared, or ho, right? Okay. So now the reason that it's in this order, because you might be mistaken, you might get these out of order, right? That would be bad, right? But you know that this is last, because when you leave, don't you always say, "Hi ho"? Don't you say that? See? Easy to remember. Easy to remember. All right. So how does this go? Are you ready? All right. So when I ask you in a second, I'm going to have you all say this with me. When I ask you, class, what's the derivative of pi over ho? You're going to say ho d pi minus hi d ho over ho ho. Okay? You ready to say it all together like you mean it? All right. Here we go. Class, what's the derivative of hi over ho? Ho d high minus hi d ho over ho ho. Wouldn't you like to do that again? Class, what's the derivative of hi over ho? Ho d high minus hi d ho over ho ho. Yeah, see, very easy to remember. Now, some people prefer the derivative of f over g is f g prime minus g f prime over g squared. Or some people prefer top times the derivative of the bottom minus the bottom times the derivative of the top over the bottom squared. Some people prefer high and low. Low d high minus high d low over low low. You know, high and low. You know, whatever. Somehow you do need to figure this out, though, right? All right. I have a proof of this that I'd like you to do. Okay. I'd like you to start by considering the function. Do this right now on your paper. I'd like you to start by considering the function h equals f over g, and I'd like you to multiply both sides by g, and then just see what happens when you take the derivative. Do it, and come back to me in a second. I assume this will take everyone no more than A minute. Maybe 2. Maybe it's longer. See what happens. I believe in you. Are you done yet?
Yes.
No, you're not. No, you're not done. I want to come around and see how you're doing with this.
Is H the derivative?
Yeah, I'm saying multiply both sides by g and then take the derivative. Right? Well, now you know how to take the derivative of h times g, don't you? See previous slide. Something we learned earlier today. H is the function that represents the function f divided by the function g, right? So take the derivative of hg
Wait, where does H?
using previous results from today. Previous results. Notice that when you do this, there's no quotient, right, to deal with, right? You just gh equals f. Just differentiate. Right, that is do this, and then differentiate both sides. I'm so sad there are not enough. I'll give you one. Yeah. You getting it? You get the option, right? It'll be the same thing again. So at the bottom has to be the bottom. But if you switch the top one, you won't get the same answer. You're not saying answer, but all right, how does your work look? How does your work look? You're differentiating. How do you do hg prime? Oh yeah, the product rule. That's right. I remember that from 15 minutes ago. Okay. All right, and then what are we doing? Let's keep our eyes on the prize. We still want to get h prime by itself. So solving for h prime looks like that. And in some ways we're done. I mean, we have the product rule here, or the quotient rule, don't we? H prime is what we seek. The only issue is we still have like an h involved, and we'd like it to be in terms of f and g. But that's okay. H is what? F over g. All right, now we're done. There it is. There's the quotient rule. Oh, except you might want to clean it up by multiplying the top and bottom by g. And you'll get that, right? Which is the quotient rule.
Mr. Chase, did you just write that squared?
Yeah.
That was really fast.
You
It was really
knew
slick.
you knew it was coming.
Yeah. I knew there was an error on the slide. All right.
The first time you taught this class?
No. I mean, yes, it's the first time I taught today. But I've taught it before, and I just remembered that error was on the slide still not correctly.
And then people like
Anyway, so that's a fun proof. It looks like we're gonna run to the bell here, but can I just give you a word of warning on one like this? The quotient rule will work, but why might you not do that on one like this? Just be aware. No, but you can do what? You can divide very quickly and just use the power rule. So, you know, there might be sometimes ways around it, but homework 5 you'll do great on. See you on Monday. Have a good weekend. I love you all.